All right. Good morning again, everyone. So maybe we can start now and then just let our classmates join in later. Um, how is homework 4 going? So we moved the deadline until Wednesday, I think, July 21st. And then, as I mentioned, feel free to answer as many problems as you can. There are 5 problems, so in the original homework, but I think I gave 2 additional problems, which reminds me I still owe you a write-up of those 2 problems. I guess one is that I want you to illustrate the use of theorem. Let me just browse quickly to it. Hold on. Was it theorem 19? Yeah. So for 3 points, you can illustrate theorem 19, which basically will require you to choose a specific vector space V with the basis B, and also a vector space W. And then I want you to define a function f defined on the chosen basis B for V onto W, and use that function to define the linear map L in the way it was defined in the proof of the theorem, and then illustrate how that linear transformation act on 3 non-basis elements in uh, in your chosen vector space. All right. So just illustrate theorem 19. Give me a specific example how you can build a linear transformation out of a function f, little f, from the set of all functions from your chosen basis for v to w. All right. And then another 3 points can be awarded if you'll be able to, let me see. I guess you need to verify. Oh, there you go. You need to verify that the map defined in example 42 is indeed a linear transformation from the set of all 2 by 2 matrices with entries over R onto the vector space of polynomials of degree at most 2 within the determinant X. Right? And then, as I mentioned, you can try as many problems as you'd like. But what I'll do is to make the denominator for homework for just 17.5. So far you can gain at most 31 points out of 17.5. And then if you'll be able to submit it before the deadline on the 21st, you'll get 20% of your score. So what would be the perfect score or the total maximum score? 31 times 26.2. So you can get 37.2 out of 17.5 if my math is correct. So yeah, take advantage of it. Now, now I realized if paano pala malalaman if I can give you a markup. um, Okay, so here's the updated. Okay, so for me to be able to know that, because we only have, let me see, kailangan ko isipin paano ko malalaman kung kailangan ko na kayong bigyan ng markup. Because once I give you a markup, that means you will not be allowed to submit anything more after the deadline. All right. So if you want to get the markup, then you need to send or to go to the assignment for homework for markup, submit a text, an inline text there saying something to the effect na, sir, hindi na ako magpapasa, you can give me the markup for this problem, all right? The criteria for the markup is that you have submitted probably if you have submitted at least 4 problems in the required out of the required 5 in the homework 4. So again, the instruction for the markup on or before the deadline. Make sure you have submitted at least 4 out of the 5 problems written in homework 4, and then go to the assignment labeled homework 4 markup. Submit an inline text saying that, sir, I do not plan to submit any other problems, so you can give me the markup right now. So you need to do that before the deadline, otherwise you won't get the markup. All right. So I'm gonna send uh, an email to the class specifying again those rules. But please take note of that. And then I think earlier today I uploaded module 4, which is about matrix representation for linear transformations. So it's already out there. The Hopefully you will be able to finish, or we will be able to finish that module by Friday, because I guess we only have how many, 2 or 3 full weeks remaining for the class. So we need to pick up the pace. Module 4 includes part 1 of homework 5. It only contains 2 problems. The first one is actually both of them are computational in nature. But problem 1 is purely uh, um, problem 1 will require a purely handwritten solution, or a how do you call it? Mano-mano nyo gagawin yung solution for problem 1. Problem 2, half of it is mano-mano, but the other half, you will use MATLAB in order to verify your solution. So kindly take a look at it. So in the meanwhile, while you're still working with probably with homework 4, make sure that you started downloading MATLAB at the background on the background, because I prefer we use MATLAB. Number 1, it's a very powerful tool. And number 2, the university provides free license for it. So para hindi nyo na kailangan magbayad or mag-download illegally ng programs. So let's take advantage of what the university offers. And the codes that I am providing will be MATLAB codes. So they will not be very complex unless we will be able to go to complex numerical linear algebra. But at least some of them are just one-liners, but they will work for large matrices. So para in the future, if I think of a very nice problem that includes a very large matrix, then you don't need to do your solutions or computations by hand. You can go to MATLAB, put a couple of lines of code, and then you'll have your results. So yeah, that's another thing about module 4. It includes two MATLAB files which you can open, and which you can play around. So hindi ako magtuturo how to program in MATLAB. You can read the help files. That's another good thing about MATLAB. Its help files are very easy to understand, so you can take a look at them. But the code so far are very basic, just a single line or two. So yeah, you can see it when you start browsing through module 4. Okay. So for now, let's continue our discussion and try to finish module 3. And we're still talking about linear transformations between two vector spaces with the same underlying field. And I guess we stopped with, we ended up last time with example 44, okay, which is the derivative map, and show that this is a linear transformation from the set of C1 functions to the set of all continuous functions. And I've said the choice of the interval here is not that important. But usually, if you are into analysis, we know that the set 0, 1 is topologically equivalent to the set of real numbers. So whatever we can do on the closed or open interval, or sorry, on the open interval 0, 1, that will probably hold true for the set of all real numbers. So basically, that's why usually we restrict our study of functions to those with domain, the open interval 0, 1 or the closed interval 0, 1. Okay. Now let's move on and see what are the salient points of this module. So basically, what we're trying to do in this example is to find the kernel and the range of the linear transformations, right? So for the kernel, it's quite easy because the kernel is a set of all elements of the domain that is mapped to the 0 vector in the codomain, right? And we have seen that the kernel is always a subspace. And actually, it's always non-empty to begin with, because we are guaranteed that the 0 vector in the domain is mapped to the 0 vector in the codomain, right? So it's already guaranteed to be non-empty. And then we have proven that it is a subspace of your domain, right? Now the range is a little bit trickier because for the range we need to collect all possible images coming from the codomain. So this is the usual notion of range we know from elementary function theory or from elementary calculus or algebra. So the range is just the set of all images of elements of the domain. So it's a little bit tricky to find the range of a linear operator. And unfortunately, the range of the linear operator carries a very important information about the linear transformation. And you will see the nice transition uh, to matrices in module 4, where we develop easier ways on how to find the range of a given linear transformation, right? But that's going beyond module 3. So let's just take a look at example 45. So in example 45, so I introduced the notion of c to the n of an interval. So this is just a set of all functions defined on the interval I or on the set I to the set of real numbers whose nth derivative exists and is continuous. So for instance, C2 of R is the set of all functions from R to R whose first and second derivatives exist and are both continuous, right? And I guess I need to correct another thing here. This should be, yeah, let's just make it, the codomain should be, to be safe, to be just a set of all continuous functions on R, right? So this linear map should be defined from C2 to C, okay, just to be sure. And then the image of a function in C2, say f, is just the second derivative of f plus the function f. And so if we want to find the kernel of this linear transformation L, we want to find all functions that satisfy this equation, right? So yung kernel, lagi nyo lang i-equate yung image ng isang arbitrary member ng domain to the zero vector in the codomain and find how should that element of the domain look like, right? So in our case, we did that image equated to the zero vector, and then we evaluate the image. And by definition of L, the image is just this guy on the left of equation 52. And the zero vector in the set of all continuous functions is the zero function, all right? So I'm not sure, but I'm not sure if you remember, but if you have taken any undergraduate ordinary differential equation class, you probably have seen equation 42. And this is actually a Poisson equation. But the general solution to 52, which we are not concerned with how we got this, just for sake of illustration, I included this. But don't worry if you already forgot how to solve equation 52. But its general solution is a linear combination of sine and cosine, right? So that means that the kernel consists of linear combinations of sines and cosines, which are the harmonic functions. And then if you remember from one of the examples, I illustrated the Wronskian of a set of functions. So if you will take the Wronskian of cosine x and sine x, you will see that that will vanish in at least one point. So that means actually what will it do? Yeah, it will never be, it is not zero for some value of x. Actually, I think for all values of x. So since the Wronskian has that property, then we can say that this set is linearly independent. And thus, the set containing cosine x and sine x is a basis for the kernel of L. And so the dimension of the kernel is equal to 2, right? And again, the dimension for the kernel is well defined because we said that the kernel is a subspace of the domain. A subspace is a vector space on its own right. It being a vector space is enough to say that it has a basis. Remember, all vector spaces have a basis. And then since it has a basis, or it is a vector space, then any two bases for it has the same number of elements, and that number of elements is what we call the dimension of that vector space. So since we found a basis consisting of 2 elements, that means the dimension of the kernel is equal to 2. All right. Unfortunately, finding the range is, I think, is difficult and more involved, so that's why I omitted it here. So yeah, I think that's the last example so far for finding the kernel and the range. So I think we will meet some more of them, but I just inserted here some definition. Before we proceed, any other, do you have any questions? Wala pa naman pong tanong. All right. Okay.
Wala
So,
pa, sir.
all right. So if that's the case, then let's move on. The next paragraph is just a bunch of definition. So if here I define what a one-to-one function mean, and then I introduced a term for it, or another term for it. I don't know if you have encountered or used this term before. Hindi ko siya ginamit pa before. Nabasa ko lang kay Golan, and it's nice to learn new terms. At mukha siyang matalino, so ginamit ko siya dito. So we say f is one-to-one or monic if and only if f of x1 equals f of x2 implies x1 equals x2. So this is the usual concept of a one-to-one function that we learned in elementary function theory. So if 2 elements share the same image, then those 2 elements must be equal to each other. So no two distinct elements of the domain is mapped to the same element of the range, right? So that's what it takes for f to be monic. And then f is onto or epic if and only if the range of f is equal to y. So if every element of the codomain has a pre-image in the domain, then we say that the function f is epic. All right. A function f that is both monic and epic at the same time is called a one-to-one correspondence or is a bijection. All right. Other terms for being monic is that f is injective or f is an injection. And then for epic, we say also that f is surjective, right? Or f is a surjection. So a bunch of terms that you can use. But I guess for the rest of the class, I'm going to use the terms monic and epic and a bijection for being one-to-one, onto, and a one-to-one correspondence, respectively. Okay. All right. And then we have here our first theorem for the day. Yes, Ma'am Rina?
Sir, pwede tayo magbigay, sir, ng isang function po na pareho pong injective at surjective? I mean, para siya po ay bijective, sir.
Bijective. Ano bang madaling example? Let me see. Siyempre, yung mga constant functions, hindi na siya kagad one-to-one, right? Because, yeah, probably I'll start with counter examples. So say f of x equals a constant is not, cannot be a surjection. Cannot be a bijection. Because for one, it is not monic because you can find 2 x's. Of course, any 2 x's will have the same function value. So hindi siya kagad monic. So hindi na siya pwedeng maging bijection. I think this is an easy example. F of x equals x for all x in R. And let's say f is considered to be a function from R to R. Okay. Now let's check being monic. So for it to be monic, it should be for it to be one-to-one, you need to consider 2 elements of the domain, say x1 and x2, being from the domain, such that their function values are equal to each other. And you want to show that x1 is equal to x2, right? So that's the definition of being monic. So you start with taking 2 arbitrary 2 elements of the domain, and suppose they have the same images under the function. And then your goal is to find your goal is to show that x1 is equal to x2, right? That's the very definition of being monic. Now, in this case, evaluate f of x1 f of x1 is equal to x1, f of x2 is equal to x2, so therefore it is monic. Okay. How do we show that this is epic? To show that this is epic, we want to show that every element of the codomain has a pre-image, right? So in this case, I'll take an element of the codomain, which happens to be R as well. So let Y be in R. And I want to find an element of the domain whose function value is equal to Y, right? Note that Y is an element of the domain. The domain of f, which I will write as dom f, is basically R, right? And f of y is equal to y. So this means that if I take any arbitrary element of the codomain, I can find a pre-image for it, or an element of the domain whose function value under f is equal to y. So that shows that the identity map f of x equals x is a bijection, right? Because it is both monic and epic. Yes, Ma'am Rina?
Sir, if that will be the case, sir, so pwede po pala natin ma-consider na bijective, sir, ay yung quadratic function, yung f of x is equal to x squared. Kasi masasatisfy po na yung pagiging injective at saka po surjective. Tama po ba, sir?
Yung quadratic ay hindi siya bijection.
Bijective.
Kasi
Surjective, di ba, sir?
hindi siya one-to-one. Tama? If you remember the vertical line,
I think, sir, hindi siya O2. Kasi for every y po, walang negative values. Kasi di ba x squared siya. So yung negative 1, walang...
Yeah, so hindi siya one-to-one kasi hindi niya masasatisfy yung horizontal line test.
Yes.
Tama po. Thank you po.
Yep. And tama rin si Jeng. You can also take a look at its range. Ang range ng x squared ay hindi R, pero set of all non-negative real numbers. So hindi rin siya surjective or hindi rin siya epic. So hindi siya pwedeng maging bijective. Another example would be any linear function. So pag meron kang ax plus b, if you look at its graph, it's just a line, right? Of course, supposing that a is not equal to 0. Yung graph niya, any linear function has a line as its graph, right? So it will satisfy the horizontal line test kasi kunwari horizontal line yan. So yung horizontal line mo will meet the graph of f only once. So that means it is monic, right? And you see that every value on the y-axis is traversed by the graph. So lagi kang may makikitang pre-image. If this is your chosen y, you can just trace the graph and see that, oh, this would be the pre-image. So lahat ng y values madadaanan ng graph. So therefore, it is surjective. So, or this is epic. So this is bijective. Okay, so you can think of it as the horizontal. If you're talking visually, you can take a look at the graph, see if it satisfies the horizontal line test, then it is monic. And see if all the y values are traversed by the graph, so that makes the function epic. And if it's both monic and epic, then it is bijective. All right. So, however, formally we won't accept visual proofs. So you need to write it down and use the definition for monic and epic in order to show that it is bijective. All right. Hopefully, in the next examples, I don't remember if I have included some examples that will require showing the monic and epic properties of a function, but hopefully we'll see them later again. All right. Okay. So Theorem 22 kind of use the concept of monic and epic. So for this theorem, we consider vector spaces over the same field F. And if you will notice, this is one assumption that we are making. I guess I talked about it last time. We are assuming that the vector spaces V and W have the same underlying field F, because otherwise I will need a bijection between the underlying fields. So kaya for simplicity, And since we are not a hardcore abstract algebra class, so we will not exhaust all generalities here. So that's why I will impose the assumption that they do have the same underlying fields, right? So Theorem 22 says or asserts three propositions. Part one, that the kernel is trivial if and only if L is monic. So when we say the kernel is trivial, that means it only contains one element, which is the zero vector in the domain. And then the range of L is a subspace of W, which I should have included somewhere earlier, but what's done is done, so let's put it here. And the range of L equals W if and only if L is epic. And I think I was thinking to delete part 3 from the theorem because it seems that it is merely a restatement of the definition of being epic, right? Kasi di ba yung range ng isang linear transformation is the set of all possible images. So if the range of L is equal to the codomain, then that is the very definition of being epic, right? For any element of the codomain W, we will be able to find an element of the domain whose image under L is equal to that element. Then that's the very definition of being epic. So probably in the revised version of the module, I'll probably remove statement 3 and just put it as an alternative definition somewhere here in this paragraph, right? But for now, let's just skip it there, and you'll see that the proof here is just a one-liner for part 3, okay? So let's walk through the proof given here for Theorem 22. Let's start with statement 1. And note that this statement is a biconditional statement. It's an if and only if statement, so the proof should have two parts. One for the triviality of the kernel, implying L is monic, and the other part we will assume that L is monic and try to show that the kernel is trivial. All right. So let's see how the proof goes. So first, I'll prove the forward implication. So here our assumption is the first statement. So we will assume that the kernel is trivial. And again, a trivial kernel means that the kernel contains only one element. And we know what that element should be because the zero vector in the domain is guaranteed to be in the kernel. So if the kernel is trivial, so its only element must be the zero vector. All right. And then I want to show that L is monic or L is one-to-one. And again, the usual way to show that your function is monic from your algebra classes is take two elements of the domain and assume that they have equal images under L. And your goal is to show that these two elements are equal to each other. Okay, and for that, probably, or actually, we will need the fact that the kernel is trivial. All right. So that's kind of the template whenever proving that a function is monic. So assume two elements of the domain whose images are equal to each other. So we'll start with that. L1 is equal to L2. And then since LV1 and LV2 comes from the vector space V, or actually in particular, LV2 is in the vector space W, then it has an additive inverse, right? Kasi nasa vector space W siya, it will have an additive inverse. Then I can add that additive inverse to both sides of the equation by the addition property of equality. And that's how I come up with LV1 minus LV2 is equal to the zero vector, right? So this is the usual transposition that we are doing since our algebra days. But the reason there is that this belongs to a vector space, thus it will have an additive inverse, then we'll use the APE by adding the additive inverse to both sides. We'll come up with this guy. And then probably one of the propositions we have earlier will allow us to put the negative sign, which is just our notation for the additive inverse. That will go inside the linear transformation. But that means LV1 plus L of negative V2 is equal to your left-hand side here. So I can do that replacement. I guess in particular, that's what you proved in homework 2 or one of the problems in homework 2. So that's fine. And then I'm going to use the linearity of L. Remember, L is a linear map. So it preserves vector addition. And so this guy can be written as this guy, all right? And now what we have is that this image, L of V1 minus V2, is equal to the 0 vector, all right? So by definition, V1 minus V2 has the 0 vector as its image. So therefore, V1 minus V2 must be in the kernel of L. All fine? Okay, I hope everything is well. Then we know what's our assumption about the kernel. We assume that the kernel only has one element. So V1 minus V2 being in the kernel means that V1 minus V2 is equal to the 0 vector in V. And again, by addition property of equality, we'll have V1 is equal to V2. And that's exactly what is required in order to conclude that L is monic. Okay? So we're halfway done with the proof of statement 1. Any questions? Hopefully hindi ganun masyadong mabilis yung pagkakadiscuss ko. I haven't had my coffee yet, so baka medyo mabilis. But I hope you guys, just let me know if I need to pause or I need to stress some points out. So, okay, let's go to the other half, which is the converse. So for the converse, again, go back to your statement here. We need to assume that L is monic and show that the kernel is trivial. Right? Let's see how it is done. Okay, for the converse, we assume that L is monic. So if it is monic, then that means that no two distinct elements of the domain is mapped to the same element of the range. Or kapag ka hindi equal yung dalawang element ng domain, therefore, hindi rin dapat equal yung kanilang function value. All right? So if W is an element of, right, I think something is wrong here. Let me just say range of L. Okay? Kasi nga pala, hindi lahat ng W ay may pre-image, right? Hindi pa tayo sure na lahat ng element ni curly W ay may pre-image. Just to be safe, if I take an element of the range, then alam ko laging isa lang yung magiging inverse image niya. Alright? Because an element of the range cannot be mapped to more than one element of the domain if L is monic. Right? So dahil si L ay monic, ang inverse image ng isang element ng range ay laging isa lang. Right? So because if there would be two elements of the domain mapped to the element W of the range, then hindi na siya magiging monic. So necessarily the inverse image of any element of the range is equal to 1. Okay? I guess I wrote that as parenthetical remarks here. And in particular, if we take W to be the 0 vector in W, that means that we're talking about the kernel. Dahil ang inverse image ng lahat ng element ng range ay may isang laman lang, it follows that the inverse image of the 0 vector, which happens to be the kernel, must contain only one element. And since the kernel must have only one element, necessarily it should be the 0 vector in the domain. So that means the kernel is trivial. Okay? And that completes the proof of Theorem 1. Theorem 22.1. All right? Everything's good? All right, thank you. Let's go to the second part of the theorem, 22.2. So here we want to show that range L is a subspace of W. So what do you think is a good approach here? Paano ko mapuprove si part 2 ng theorem? Any suggestion?
Sir, tama ba pag subspace kung pwede po natin ipakita yung dalawa? Yung sa addition po at saka sa scalar multiplication?
Yes, that's correct. In order to show that a subset is a subspace, we can use the Compact Criterion, which is, I think, Theorem 3, if I'm not mistaken. So all we need to do is to show closure under addition and scalar multiplication, right? And hopefully that's what I did here. Tingnan natin kung yun nga ba ginawa ko. Yes, I think so. So in order to show that the range of L is a subspace of W, I want to show that the range of L is closed under vector addition and scalar multiplication. So for the first part, I will assume two elements of V. And so if there are elements of V, actually, I want to show that range L is a subspace. So I will consider two elements of the range and show that their sum is also in the range, right? But if W1 and W2 are in the range of L, then there will exist elements of the domain whose image under L are equal to W1 and W2, right? So in particular, there will exist a V1 and V2 such that LV1 is equal to W1 and LV2 is equal to W2. Kasi si W1 and W2 ay element ng range. So sure tayo may elements ng domain na pag kinompute ko yung function value nila, equal sila kay W1 and W2 respectively. All right? And now our goal is to show that W1 plus W2 is in the range of L. So what I'll do is take a look at W1 plus W2 and how it looks like, right? But I can change W1 into LV1 from this assumption. So W1 was changed to LV1 and W2 was replaced by LV2, which is fine. And then we'll use the linearity of L. So that means W1 plus W2 is equal to L of V1 plus V2. And what have we shown here? We have shown that W1 plus W2 is the image of V1 plus V2, right? But obviously V1 plus V2 are in the domain V, right? By closure of V under vector addition. And therefore W1 plus W2 is in the range of L. And that is true because we have found an element of the domain, namely V1 plus V2, whose image under L is W1 plus W2. Okay? And now that's closure under addition. Now let's try closure under scalar multiplication. So for closure, I will assume an arbitrary scalar alpha and show that alpha W1 is in the range of L, right? So alpha W1, again, our assumption is that W1 can be written as LV1. And then I'll use the linearity of L. That means the scalar alpha can go inside the linear map L. So that means this guy is equal to L of alpha V1. And what have we shown here? We have shown that the scalar multiple alpha W1 is the image of alpha V1 under L. So that means alpha W1 is in the range of L, proving that that the range of L is indeed the subspace of W. Okay. So this theorem has some nice implications, but some students will say hindi siya nice kasi we have proven that the range of L is a subspace. That means the range of L is a vector space on its own right. If you have a vector space, it's natural to talk about the basis or a basis for that subspace. And if you have a basis, if you have a vector space, it's natural to ask what's the dimension of the range of L, right? And that will be a bad news for us because we said that finding the range is tricky enough. Finding a basis for the range is also hard, right? Or will also be hard for complicated linear maps kasi ang hirap na maghanap ng range tapos hanapan pa siya ng basis. What we know about basis, dapat siya linearly independent, saka dapat ini-span niya yung vector space. It is sort of easy to show that a given set is a basis for a vector space. However, if you'll be starting from scratch, mahirap mag-isip ng basis out of nothing for a vector space, right? And that's one difficulty about finding the dimension of the range of L. But we'll look at a couple of examples. But again, in Module 4, we will invent some ways on how to compute the dimension of the range much easily. All right. So that would be something to look forward to in Module 4. Okay. And as I have mentioned, Theorem 22.3 is sort of a restatement of the definition of being epic. So yeah, that's why I'll probably remove it in the revised version of the handout or the module. Okay. All right, and then page 34 again. I have a couple of remarks here, but some terms again. If your if your monic function is a linear transformation, then we call it a monomorphism. I remember a linear transformation, and another term for them would be homomorphism. Homomorphism. It's a morphism or a function because it morphs an element of the domain into an element of the codomain. It's homo because it preserves the linearity property of the vector space insofar as vector addition and scalar multiplication are concerned. So that's why they are called homomorphism. They preserve the structure of the domain into the codomain. And if you add the term monic, then sort of it's monomorphism, mono plus morphism. And then if you have an epic linear transformation, it's called an epimorphism. And then if your linear transformation is both a monomorphism and an epimorphism, then it is an isomorphism. Okay, so just some more terms to remember. Pero sana na-appreciate nyo paano nagpapangalan yung mga mathematician ng mga terms. They are not just conjured out of thin air. Usually meron siyang pun into it or meron siyang reason bakit gano'n yung tawag. So I guess you have seen these terms in your modern algebra classes, tama ba? At least in the context of groups. Meron kang monomorphism, epimorphism, and isomorphism between groups or rings or fields. So ganun din yung idea rito. Pero the property that we are preserving are vector addition and scalar multiplication, or basically the linearity properties of our vector space. Okay. Now,
Sir, may tanong ako.
Oh, sure. Go.
Kasi di ba ganit ang mga terms na to may morphism lahat sa huli. Ano po yung anong po yung condition for automorphism?
Ang automorphism ay isang pag automorphism dapat siya ay though hindi natin kakailanganin yung automorphism so far. Morphism, so ibig sabihin function siya, right? So function siya kaya siya may morphism. Auto meaning from itself to itself. So an automorphism is a linear transformation from a function to itself.
So actually, parang mga R to R, mga ganyan, sir.
Yeah, pero dapat isomorphism siya. So dapat siya ay isomorphism from a function or from a vector space V onto itself. So an automorphism is an isomorphism between a vector space and itself. So you can think of an isomorphism simply as a rearrangement of elements of your set. Okay? Though in linear algebra, hindi tayo masyadong concerned about automorphism kasi gusto nating tinitingnan yung equivalence between vector spaces. So we know that a vector space is equivalent to itself via the identity isomorphism, which is an automorphism. Pero yeah, ganun yung pwedeng tandaan yung napakaraming terms sa algebra and mathematics in general. Okay? Now, if there is an isomorphism between two vector spaces, if you can define a bijective linear transformation from V to W, then we say that V is isomorphic to W, and we use this notation, right? So si V ay isomorphic kay W. So ibig sabihin, if V is isomorphic to W, that means they are sort of equivalent. They are sort of equivalent in the sense that you can think of elements of V as, or elements of W as elements of V disguised in another name. So you can think of it as a relabeling of the elements of W. So parang dinisguise lang natin yung elements ni W by using names from V and vice versa. Okay. Now there is an interesting. Actually, you can show that being isomorphic is an equivalence relation, but we're not into that abstract of an algebra. So yeah, I'm not sure how much we will deal about isomorphic things, but I just want you to see the connection between modern algebra and linear algebra, right? Kasi dapat mas general yung linear algebra. So lahat ng pinag-aaralan natin dito, insofar as structures of vector spaces are concerned, will just be a specification of the things you learned in modern algebra. Okay? Now, let's move on. Okay. Now, proposition 23 is sort of a technical result. So, but before that, I guess I mentioned that the inverse image of a non-zero element of the codomain is not a subspace of W. However, it is almost a subspace because proposition 23 will show that that L inverse of W is just the translation of the kernel by some fixed element of the domain, right? So let's see how it goes. So for proposition 23, we are assuming V and W to be vector spaces over a field F. And then we consider a linear map between the two vector spaces and W to be an element of the range. Tapos magfi-fix tayo ng element ni V, okay, from the inverse image of W. Then the inverse image of W is a translation of the kernel because all inverse, the inverse image of W is just V, a member of the inverse image, plus an element of the kernel. So lahat ng element nito ay translated version lang ng elements ng kernel. Okay? Now let's try to prove it. So here we want to prove equality of two sets. And remember, when you want to solve to prove the equality of two sets, you need to show that one is a subset of the other. Okay? Now, in this statement here, I want to show that this set is a subset of L inverse of W. Okay? So what I'll do, in order to show that this is a subspace of this, it's a subset of that guy, so this is what I want to prove. I'll take an element of this. So kukuha ko ng element ni V0. Oh, by the way, V is a fixed element. Si V ay finifix, Si V ay naka-fix from the beginning. So dapat siguro inuna kong i-state yung V. So let me just take note of that. That should go first. So si V yung fixed element ng L inverse. Then kukuha ko ng arbitrary image ng kernel. Kasi gusto ko ipakita na any member of this guy is a member of the left-hand side. Okay? So V is fixed. V0 is an arbitrary element of the kernel. I want to show that that is in the inverse image of W. But what does it take for an element of the domain to belong to L inverse of W? Ibig sabihin, by definition of L inverse, dapat pag kinompute ko yung function value ng element ng domain na yon, dapat equal kay W, right? Because again, L inverse of W is the set of all vectors in the domain whose image under L is equal to W. So in order to show that V plus V0 is in L inverse, I want to show that this guy is equal to W. And let's see how it is done. Okay, the first step is to use the linearity of L. So I can write the image as the sum of two images. But what do we know about V0? V0 is in the kernel of L. So that means L of V0 is equal to the 0 vector in W. And since that is the case, we'll have LV0 plus 0W, the 0 vector in W will give us LV. But what is LV? Remember, V is a fixed element of L inverse of W. Sure tayo si V nasa inverse image ni W, so L of V must be equal to W. Correct? And that shows that the right-hand side is a subset of the left-hand side. For the reverse inclusion, we will take an element of this guy and show that that's of this form. So gusto kong ipakita pag kumuha ko ng isang element ng L inverse W, I want to show that I can write that as the fixed element V plus an element of the kernel. Okay? So there's a little there's a nice trick on how to show that, because ang kailangan kong hanapin ano dapat yung element ng kernel na i-add ko kay V, na arbitrary member ng L inverse W. Okay? So I'll start with that. I'll consider a V in L inverse of W, and we want to show that, or actually ito pala yung fixed element natin from the beginning. I'll take another arbitrary element V prime of L inverse of W. That's L inverse of W. At gusto kong ipakita si V prime ay pwede kong isulat as V plus V naught para ma-prove ko yung reverse inclusion. Okay? Now note that V naught can be written as V plus V, or that's what we want to show. We want to show that V prime is V plus V naught. Pero note, this is a nice trick. V naught can be written as this sum. Okay? Parang ano bang ginawa rito? Nag-add and subtract ka lang ng V. If you simplify the right side using associativity and probably commutativity of addition in vector spaces, will give us the left-hand side, right? Kasi itong V na to at yung minus B will cancel each other out. But the nice thing about this way of writing V prime is that my guess is that this could serve as my V naught, because we want to show that V prime is the fixed element V plus an element of the kernel. So if we will be able to show that this guy belongs to the kernel of L, so this qualifies as our V naught. And then we are done, okay? So to check if indeed this is an element of the kernel, I'll compute its function value and hope that this is equal to the 0 vector in W. So from here, I'll use the linearity of L to write it as a sum. But what do we know about V prime and V? V is the fixed element of L inverse W. V prime is an arbitrary member of L inverse W. So therefore, this guy is equal to W, and this guy is also equal to W. And W minus W is equal to the 0 vector. Therefore, V naught, which is V prime minus V, is an element of the kernel. And so we were able to show that any arbitrary element V prime of the inverse image of W under L is a sum of the fixed element V plus a kernel element V naught, where V naught is equal to this guy. And so that proves the equality of the two sets. So proposition 23 is very useful in solving equations in inverse problems and also in statistics. So that's why I included it here. I was planning to do a more detailed discussion about this in the context of matrices, but I don't think we can reach that point because we only have I think 2 full weeks or 3 full weeks for the class. So yeah, but hopefully we'll get there. Pero yeah, it's the translation of a function is usually is used in several application areas. That's why we adopt a certain notation for the translation of a set by an element. So we write V plus a set U to be the set of all elements of U translated by an element of V, translated by the vector V. So V plus a set U is the set of all vectors of the form V plus an element of U. So I hope we can go back to this, but yeah, if not, then just bear them in mind, and then you might probably encounter them in statistics or in your research disciplines. but okay. I'll skip discussing the affine transformation. You can read it here. Though I made a I think I made a false promise here. Let me see. Yeah, I said I'll ask you to prove some facts about the set of all affine transformation in the homework, but I forgot to include one. So yeah. So that's just additional optional reading. Okay. Let's go to Theorem 24. Theorem 24 tells us about the existence of an inverse mapping, right? So let's see why. So we'll start with a linear transformation, actually not just a linear transformation, but an isomorphism L between V and W. Okay. Then it claims that there exists an isomorphism M, okay, from W to V, such that M circle L is the identity map, or in other words, M circle L of V is equal to V, and L circle M of W is equal to W for all V in V and W in W. So basically, if you will recall, this is what we call, or the isomorphism M is what we call the inverse of the isomorphism L, right? So this means that for a function, or for a linear transformation to have an inverse, it must be an isomorphism, right? At alam nyo na yan from elementary algebra, right? So the inverse function will exist if and only if your function is bijective, right? Kung siya ay one-to-one and onto. Now, if you add the requirement that your function should be linear, then it takes an isomorphism to have an inverse. Okay. Now, should we go over the proof? Let me see. Is there a salient point in the proof here? Okay. Yeah, probably it won't hurt if we'll browse through the theorem. Okay, so let's see what are the important points of the proof of the theorem. So we start with an isomorphism L. And here I am defining what the mapping M is, right? Because the theorem is a proof of, is an existence theorem. It tells us that there exists an isomorphism M. So in the proof, we can do it via construction. I mean, we can construct what the function M is, right? So here, I define the function M from W to V to be the map such that M of W is equal to V if and only if L of V is equal to W. Okay? So yan yung definition ko about the function M. And this is a well-defined map because kung given ako ng W, lagi ng W in W, right? Dahil si L ay isomorphism, so therefore L is epic, right? So that means for every W in W, I can find a V in V such that L of V is equal to W, right? So laging makikita kong V kay V na ang image under L ay equal kay W by L being epic. At dahil yon ay nangyayari for every W, then I can define M of W to be equal to V. Okay. And also, if I have, and then every W will be mapped to exactly one element of V. Kasi di ba dapat si M function muna. So kung si M ay function, dapat, or para si M ay maging function, dapat pag nag-plug in ako ng isang element ng domain, laging makukuha ko ay isa lamang element ng range, right? Bawal yung W ma-map sa dalawang magkaibang element ng range. So in this case, that is true because L is monic. So ibig sabihin, kung si M of W ay equal kay V1 at si M of W ay equal kay V2, para si M ay maging function, dapat si V1 ay equal kay V2, right? Dapat every element of the domain is mapped to exactly one element of the codomain. Now, to prove that this is well defined, I'll use the fact that L is monic. So why is that true? This happens if and only if L of V1 is equal to W, and this happens if and only if L of V2 is equal to W, right? That's the definition of M. But here we see that LV1 is equal to LV2. They're both equal to W. But we know that L is monic. So that means that implies that V1 must be equal to V2. So that means W is indeed mapped to a single element in the codomain. So that means M is a well-defined mapping. Function siya talaga with domain W. And that's due to the fact that L is both monic and epic. Now, after proving that M is well-defined, let's prove that M satisfies the properties mandated by the theorem. That is, M circle L of V is equal to V, and L circle M of W must be equal to W. So let's see. Let's compute M circle of L of V. Now, by definition of function composition, this guy is equal to M of LV. But what is L of V? L of V is equal to W, right? Provided W, I guess that's how we define L, right? How we define M. So that means L of V is equal to W, okay? But what is M of W? M of W is equal to V if and only if L of V is W. But again, we said W is L of V. That's just what we call L of V. And by definition, in 53, definition of M of W must be equal to V. So indeed, M circle L of V is equal to V. And then the other condition in the theorem, we want to show that L circle M of W is equal to W. Okay? And by definition of function composition, this guy is just L of MW. And then suppose M of W is equal to V. Okay? So that's why I will replace M of W equal to V. Nothing fancy there, just change of variable. I just said, okay, let me call M of W be equal to V. That's how I got this. But what is L of V? Well, if we go back to 53, if M of W is equal to V, and that's what we assumed in here by change of variable, right? That means that will imply that L of V is equal to W. So that means L of V will be equal to W. And hence, L circle M of W is equal to W. Kaya medyo madaya yung pagkaka-define natin ng M. So that's how we forced L circle M and M circle L to be the identity maps in the respective vector spaces. Okay? So na-prove na natin that M is well-defined, that M satisfies this condition. Now, what's left to be shown is that M is an isomorphism. Okay? Let me see how I did that here. I guess first I started showing that M is a homomorphism to begin with. So I want to show that M is a linear map. So that's why that's why I look at M of W1 plus W2 here for arbitrary members W1 and W2 of W, right? So if W1 and W2 are in W, and remember that L is epic, so there will exist V1 and V2 such that LV1 is W1 and LV2 is equal to W2. Okay? And using the fact that L is a homomorphism, then W1 plus W2 can be written as a sum, and this sum can be written as the image of a sum. Ginamit ko lang yung pagiging linear transformation ni L. And this will allow me to evaluate M of W1 plus W2, right? Kasi remember from equation 53, ang definition natin sa M of W ay equal kay V provided L of V is equal to W. Okay? But I know that L of V1 plus V2 is equal to W1 plus W2. So pag nilagay ko si W1 plus W2 inside M, I should get back V1 plus V2. By the way, I defined M in equation 53. And so this statement holds. And so that proves that, but by the way, V1 by assumption is equal to MW1 because W1 is equal to LV1. Remember, parang pinapasok ko lang to sa M. And then sabi natin M of LV1 will just return V1. That's how I got this replacement here. And then this statement implies that V2 is equal to M of W2. Okay? So ultimately, we have shown that M of W1 plus W2 is the sum of images under M. Thus, it preserves vector addition. And then I'll use a similar argument to show that it preserves scalar multiplication. So if alpha is any scalar, and then the fact that L is a linear transformation, imply that L of alpha V1 is equal to alpha of W1. And so if I will evaluate M of alpha W1, and remember si M, binibigay niya lang sa atin ano yung pre-image ni alpha W1 with respect to the function L, right? So that means M of alpha W1 is the element of V whose image under L is alpha W1. But from the preceding statement, we said that alpha W1 is equal to L of alpha V1. And so it follows that M of alpha V1 is alpha of V1. And then but remember, V1 from above is exactly M of W1. And so here we have shown that the image of a scalar multiple is the scalar multiple of an image. And so indeed, M is a homomorphism. And then there's still two things left to be shown. We need to show that M is an isomorphism. And for that to happen, M should be monic and M should be epic. Now, for being monic, I'll consider two elements of the codomain or of the range. Yeah, but probably it's better to say range of L instead of W. If W1 and W2 are elements of the range of L, sorry, not range of L, but range of M, because we are showing that M is monic, right? So I'll take two elements of the range of M, such that, not range of M, tama ba? Range of M. Hindi. Dapat ito ay domain. So tama yung W kanina.
L yun sir.
Yeah. So dapat siya ay W. Kasi pinapakita natin na si M ay monic. Kung si M ay monic, dapat pag kumuha ako ng dalawang elements ng domain niya na equal yung function values, dapat equal si W1 and W2, right? So that's why I can take W1 and W2 to be elements of W, such that M of W1 is equal to M of W2. And say their common value is V, right? By definition, in 53, that's the definition of M, then M of W1 equals V implies that L of V is equal to W1. And again, by definition of M of W2 being equal to V is the same as saying that L of V is equal to W2, right? And what do we have here? We have the same element of V mapped to the same elements of W. But L is a homomorphism, so it is a function in the first place. So that means if LV is equal to W1 and LV is equal to W2, then W1 is necessarily equal to W2. Kasi every element of the domain in a function must be mapped to the same element of the codomain or of the range. So that forces W1 to be equal to W2. So we have shown that if M of W1 is equal to M of W2, then necessarily W1 must be equal to W2. Hence, M is monic. And then lastly, we want to show that M is epic. So for it to be epic, we want to show that every element of the codomain is in the range. So I'll take an element of the codomain of M, right? So ito yung codomain ni M, right? Because remember, M is a function from W to V. Gusto kong ipakita na si little v ay may pre-image under M. So, okay. However, since V is in V, and remember that L is epic. L is a function from V to W, right? So dahil si little v ay na kay curly V, and si curly V ay yung domain ni L, so there will exist an element of W such that L of V is equal to W, right? So by equation 53, M of W then is equal to V. So that means every element of the codomain of M will have a pre-image little w in W. So that means the range of M is the entire V. Kasi napakita ko na pag pumili ako ng arbitrary member ni V, lagi ako may makikitang member ni W such that M of W equals V. So therefore, every element of curly V has a pre-image in W. In other words, the range of M is equal to V, making M epic. And so after 5 steps or 5 things, we have proven that M is an isomorphism. And the isomorphism L plays an important role because M is the inverse of the linear transformation L. Okay, so and I kept on discussing some things about the inverse, but these are things that you know from elementary algebra, right? Yung inverse function, ang ginagawa niya lang, nire-reverse niya lang or ina-undo niya lang yung ginagawa ng function, ng original function, right? Because if you have a function f, then f inverse of f of x will just be x, right? So it will just undo what the given function f does. But you already know that may binigay lang tayong additional property for the function. We just say that this would be just, both of them will be linear transformation. So the major takeaway from that theorem is that the inverse of an isomorphism is also an isomorphism. So if your linear mapping is epic and monic, then its inverse will also be a homomorphism that is epic and monic. All right. Okay. And then I guess we are near the end of the module. So here in definition 8, I'll just go back to the fact that we have established that the kernel and the range of a linear transformation are subspaces of the respective vector spaces, right? And so if they are vector spaces on their own rights, then we can talk about their dimensions, okay? And they are very important, or there are nice properties of the vector spaces that are, or that can be gleaned by looking at the dimensions of these special subspaces. That's why their dimensions are given special names. In particular, the kernel, or the dimension of the kernel of L, is called the nullity of L, denoted by null of L. So null of L is the dimension, or the nullity of L is the dimension of the kernel, while the rank of L is the dimension of the range of L. And probably this rings some bells insofar as your undergraduate linear algebra is concerned. Parang ito rin yung sa matrices, right? So matrices has nullity and rank, meron kang full rank, and so on. In Module 4, we'll talk about the relationship between the nullity and the rank of linear transformations and the nullity and rank of matrices, right? But for now, for us, the nullity and rank of a linear transformation is basically the dimension of the kernel and of the range of the linear transformation, respectively. So the rest of the module is focused on illustrating how to compute the null and to compute the nullity and the rank of a linear map. So hold on. Magana muna tayo. 30-second break. I'll just need to take some water. Okay, before moving on, kumusta naman? Patapos ng SEM. Busy na ba kayo? That's why I'm thinking to lessen the number of homeworks, by the way. I remember in the syllabus I said we'll have around 9 or 10 homeworks, but I'm thinking to bring it down to 5. Probably 5, 6, or not 5, kasi may homework 5 na. 6, 7, or 8. Okay lang ba yun? If we lessen it to that, magiging 7 homeworks na lang siya. 7 or 8. Actually, I can even go down to 6. What do you guys think? The drawback, gusto kong i-present sa inyo yung pros and cons. Okay. Though I see good, nice reactions from you guys. Ang magiging con niya ay lalaki yung weights ng bawat homework. So if we will have just 6 homeworks, I guess we'll have minimum of 6 or probably 7, 6 or 7. Lalaki yung weight ng homework 1 and homework 2. I guess you guys felt better with homeworks 3 and 4. And I hope you'll also feel better with homework 5. So medyo lalaki nga lang yung weight ng homeworks 1 and 2. But again, don't be too worried about computing your grades using your raw scores in the homework, because I said I will grade you on your progression. And I guess that's why I hope you guys followed my suggestion in your naming of your homework submissions. Kasi in giving your final grades, what I'll do is compile all your homeworks from day 1 until the last day and see how you progressed or how you went about the homework. So I want to see the effort. I want to see your progression from day 1 until the last day of class, and that's how I will grade you. So yung sinabi ko in the syllabus na the criteria will be the average of your homework percentages, and that we will use the standard transmutation table given by OU. That's just for formality, but I'll do some, how do you call it? Standardization ba siya? May tawag eh. I forgot the term, but yeah. I'll definitely consider the learning curve in a course, because basically, based on your on the things that you shared, most of you did this a while back, probably years ago, or some of you probably haven't done proving before. So that's why I really appreciated all the work that you put into the course, and I hope to give justice to that when I give your final grades. So do not believe what I put in the syllabus. Probably I should not be recording this, but yeah, don't believe the grading scale there. I'll probably post my grading criteria during the last week of classes for you to be guided. And what I'll also do is to post your grades probably a couple of days before the deadline for submission of grades, so that you can inquire about it, and then you can probably check it if that's fine with you, and then we can talk about it. Okay? But yeah, okay ba yun? Let's just do it probably minimum of 6, maximum of 7. Or you want to go with maximum of 8. I think the ideal is 7, but I can go as low as 6 or as high as 8 homeworks. Kasi meron na tayong homework 5 for module 4. And then we have the final homework na ibibigay ko sa last day of classes. So that makes at least 6. But I probably can give a homework 6. So that makes a total of 7. Okay, I hope that's okay. All right. So, okay ba yan? Yeah, I see hands clapping. So I guess I'll do that. Hold on, guys. Can we take a 2-minute break? I'll just need to go to the bathroom. Okay, so I'm back. Let's continue. Example 46. So example 46 considers the linear map L from the set of all 2x2 matrices with real numbers as entries to R squared. So it maps a 2x2 matrix to a 2 vector in R, right? And the linear transformation is defined this way. The image under L of a matrix with entries A, B, C, D is equal to the 2 vector A plus B and then C plus D, right? So you can verify that this is a linear transformation as an exercise. Pero hindi na siya additional problem kasi meron na tayong problem similar to this earlier. So now let's take a look at the kernel of L, right? So again, for the kernel, we need to equate, we need to take an arbitrary member of the domain and say that this element of the domain will be in the kernel if and only if the function value of that element of the domain is equal to the 0 vector in the codomain. The codomain is R squared. So the 0 vector in R squared we know is 0, 0, right? So we'll simply need to equate L of A, B, C, D to the 0 vector 0, 0, all right? But if we evaluate this guy, that will just give us A plus B, C plus D by definition of L, right? And then equate that to the 0 vector. That will tell us that A plus B must be equal to 0 and C plus D is equal to 0. And then we need to solve for conditions on A, B, C, D. And that conditions will be conditions for that matrix to be in the kernel of L, right? From the first equation, we'll see that B is necessarily equal to negative A. From the second equation, D must be equal to negative C, and A and B are, hold on, parang may mali. Yeah, may mali nga rito.
So yung kernel L nyo po naging A negative A tapos B negative B, hindi.
Yeah, so,
Ano nga ba yan? Dapat A A negative B tapos C negative D?
C negative. Well, yeah, probably it's a good, yeah, it's a blessing in disguise para makita natin paano siya binubuo, right? So here we see that in the conditions for A, B, and C, D, A, B, C, and D, we have seen that B must be equal to negative A and D must be equal to negative C, right? So that means A and C are free variables. So kasi walang ibang condition kay A and C aside from being in the set of real numbers. And the only conditions are on B and D. So kapag kami naisip ka na fix na A and C, then B and D can be computed accordingly, right? In that sense, again, A and C are free variables. So we can retain A and C, all right, in our matrix because they are free variables, no conditions required in them, except that they should belong to the set of real numbers, okay? And then si B necessarily is equal to negative A. Ibig sabihin, dapat si B ay equal kay negative A. And si D, which is your entry on the second row and second column, must be equal to negative C. Okay? So that's how the kernel should look like. Nag-update ba yung screen ko sa inyo?
Hindi, sir.
Yeah.
Blank pa din yung kernel L.
Hold on. Let me see what happened. Kasi nasulat ko na siya. So, ibig sabihin, na-disconnect yung iPad ko. Pero, let's see. Okay. But the kernel should be of the form A negative A, C negative C, right? So, 1 entry should be A. First row, second column should be negative A. Second row, first column should be C. And then second row, second column should be negative C. Okay? Ayan. Mukhang nag-update na siya.
Yes, sir.
Right. So parang...
Opo, sir.
Well, magpapalusot ako. No? Tama rin pala yung pagkakasulat ko kanina. Though hindi siya directly nagpa-follow dito. Pero you see that the actual form of the kernel is that dapat yung entries dun sa first row ay negative of each other. And then yung entries sa second row should be negative of each other, right? But para mag-follow siya from what from the equation that we derived, kailangan ko itong palitan ng C and negative C. Okay, medyo delay yung reaction, pero yeah, in the bottom paragraph, in the bottom sentence, I change A to be equal to A negative A and C negative C. There you go. And then here we see that every element of the kernel can be written in this way, right? Kasi yun dapat yung form ng kernel. And in order to find the nullity of L, I need to find a dimension, or to find the dimension for the kernel of L. And to find the dimension of the kernel of L, I need to find a basis for ker L. Okay? Now, paano makakakuha ng basis para kay ker L? Kailangan ko makakita ng linearly independent set na nag-span sa buong kernel. Alright? But note that any element A of the kernel, which is of this form, can be written as a linear combination of this form, A and C. Tama? So that means every element of the kernel is a linear combination of the matrix A1 and the matrix A2. Okay? Kasi lahat ng elements ng kernel, ganito yung itsura. Pag ganito yung itsura niya, pwede ko siyang isulat as a linear combination of this form. Tama? And what can we say about A1 and A2? Ito si A1, ito si A2, then they are not scalar multiples of each other. All right? And since they are not scalar multiple of each other by the Steinitz replacement theorem, the set containing A1 and A2 is a basis for the kernel of L. Okay? Since A1, A2 comprise a basis for Ker-L, then we can say that the dimension of the kernel of L is equal to 2. Therefore, the nullity of L is equal to 2. Okay? And you see how tedious it is to find the nullity of a linear transformation. We need to find the kernel, find a basis for the kernel, and count the number of elements in a basis for the kernel. Yes, Ms. Au?
Sir, when you did kanina yung A and C for the kernel, is it also possible instead of in terms of A and C, in terms of B and D?
Yes. Mm-hmm.
So either. Okay po. Sige. So here, pwede naman sir in terms of B and D also. I'm just asking if okay lang din yun. Okay,
yes.
sir. Salamat po.
Pero makukuha nyo same form din. Nandito lang yung negative sign.
Yes, sir.
Nandito. That's fine. Yep. Mm-hmm. And then posibleng, tama ba? Magiging iba ba yung basis? But it doesn't matter kasi kahit ano namang basis, magkakasing dami naman sila ng laman, right? So you can think of other bases aside from A1 and A2. That's fine. Pero the invariance theorem for dimensions will tell us na kahit iba-iba tayo ng basis na makukuha, pare-parehas naman dapat yung dimension, right?
Thank you, sir.
So, yeah. So, nullity is equal to 2. So, kung medyo tedious na yung pagkuha ng nullity, finding the rank is, I think, much more tedious. Because now, we need to find, first, how does the range of L looks like, right? And so far, we are just dealing with guesses for the range of L and show that indeed that forms a range for L. Okay. Now here I am saying that mukhang dun sa itsura ng image. Okay. Kung i-analyze ko how the image looks like, the image is just comprised of the first component being the sum of the rows of the matrix in the domain. The second component is the sum of the second row in second row of the matrix in the domain, right? So kung ganito yung itsura ng range, kaya ko bang makuha lahat ng vectors in R squared? And if we just examine how this image looks like, that seems to be the case. Kasi kung meron akong real number xy, okay, si x, kaya ko siyang i-break down into an a plus b, right? I can do that for any real number. I can write x as a plus b. I can also write y, any real number y, in the form c plus d. Okay, pwede ko siyang i-split into 2. So it seems that any element of R squared can be written as a pre-image of a matrix coming from the domain. Okay, and let's prove that. So here I am claiming that that any two vector AB belonging to R squared will be in the range. So that will happen if and only if we can find a matrix of this form such that L of A is equal to B. Okay, but L of A is equal to B if and only if C plus D, E plus F is equal to AB. Right? And how can we realize AB to be of this form? Well, I can say that, I can take C is equal to A, B is equal to E, and then D and F is equal to 0. So pag kumuha ka ng isang XY dun sa codomain, pwede ko siyang isulat as X plus 0, Y plus 0. And then this will be basically the image under L ng X0, Y0. Okay? So that means any element in the codomain can be written as the image of an element of the domain under L So therefore, the range of L is the entire vector space R squared. Okay. And you see that there's another way to see xy as an image under L. So it can also be 0x, 0y. And this proves that L is not monic. Because if x and y are non-zero, okay, then the vector xy can be written in two ways as an image under L. So, ibig sabihin si L hindi na monic kasi may dalawang magkaibang element ng domain, namely x0, y0, and 0x, 0y. It doesn't matter, that's just an incidental finding here. L is not monic, but L is epic, right? Kasi lahat ng element ng codomain, R squared, ay isang image by an element of the domain. So the range of L is equal to R squared, the codomain. So L is monic, but L is not monic, but it is epic. Yes, Miss Au, you have a question?
None, sir. That was kanina pa po. Sorry po.
Okay, no problem. All right, so is that clear how we found that that L is epic? So dahil si L ay epic, ang range ng L ay R squared. And do you guys remember what is the range, what is the dimension of R squared? So kapag ka meron kang vector space V to the N, ang dimension niya lagi ay N, right?
2.
So R squared, N is equal to 2, so dimension niya ay 2, all right? So the dimension of the range is equal to 2, that means the rank is equal to 2, okay? Now let's take a look again at the nullity. The nullity is 2. The rank is 2. If we add them together, nullity plus rank is 2 plus 2, so we get 4. And if we go back to how L is defined, okay? So ang nullity plus rank ay equal kay 4. Ano yung dimension ni M2? Do you remember?
4.
Set of all 2 by 2 matrices.
4.
4. And then dimension of this is 2, right?
2.
It looks like yung nullity plus rank adds up to the dimension of the domain. But just one observation. In math, we cannot draw any conclusion from that, though we kind of build this guess that the rank and the nullity must add up to the dimension of the domain. But let's investigate further and look at another specific example, example 47. So example 47, I consider the transformation L from P1 to P1 bracket X. So this is just a mapping on the set of all polynomials of degree at most 1 onto itself. Wherein if I have a polynomial ax plus b, its image under L is defined to be 2bx minus a. Okay? So yung ax plus b, pag in-input ko siya sa homomorphism L, ang makukuha ko ay 2bx minus a. Again, it would be a nice exercise to check that L is indeed a linear transformation on the given vector space. And then if we want to get the kernel of L, kailangan nating mahanap lahat ng polynomial whose image under L is the 0 vector. But remember, ang itsura ng lahat ng polynomials in P1 bracket X ay ax plus b, right? Because this is the set of all linear functions and constant functions. So they can be written in the form ax plus b, where a and b are real numbers. Okay? So if I will put ax plus b inside L, by definition, I will get 2bx minus a. And if I want P to belong to the kernel, then I will say that 2bx minus a must be equal to the 0 polynomial. But the 0 polynomial can be written as 0x plus 0. And two polynomials are equal to each other if and only if the coefficients of the powers of the indeterminate are equal to each other. So that means the coefficient of x must be equal to each other. So we must have 2b is equal to 0. So typo here. let me just note that there was a typo here. So 2b must be equal to 0, just equating coefficients. Negative a must be equal to 0. Constants should be equal to each other. We get this. And so we'll get b is equal to 0, a is equal to 0. So the only way for a polynomial to be in the kernel of L is that if a and b are both equal to 0. But what are a and b? A and b are the coefficients of x and the constant coefficient respectively. So any element of the kernel should be of the form 0x plus 0, which is just the 0 polynomial. So here we say that the kernel only contains the 0 element. So we say that the kernel is trivial. Kasi ang laman niya lang ay yung nag-iisang guaranteed element, which is the 0 vector in the domain. Okay? And then by convention, we say that, I don't know if we mentioned it earlier, but by convention, we say that the dimension of the set containing the 0 vector is just 0. Okay, so that's our convention. So therefore, we say that the nullity of L is equal to 0 because the kernel is just a trivial vector space, and by convention, the dimension of the trivial vector space is equal to 0. So nullity is 0. All right. Now, I want to see what the range of L is. Now, what I'll do is to take a generic polynomial Q in the codomain, and I want to see if there's an element of the domain whose image under L will be equal to Q. All right. Since Q is a generic element of the codomain, it would be of the form Cx plus D. And my goal is to see, meron bang polynomial, say Ax plus B, doon sa domain, na pag pinasok ko kay L, ang magiging sagot ay si Q. And true enough, if you'll do some algebra, you can take P of X to be negative dx plus 1/2 C. Okay? Now, because if I will plug this P inside L, that will give me Cx plus D as the image. So that means any generic polynomial belongs to the range of L. So that means that the range of L is the entire vector space P1 bracket X. And so if I want to get the rank of L, I need to find the dimension of the range of L. Pero ano nga yung dimension ng P1 bracket X? Remember, si P1 bracket X, isang basis para sa kanya, o yung canonical basis para sa kanya ay 1x, right? And this has 2 elements. So that means that the rank of L is equal to 2. Then let's take a look at the sum of the nullity and the rank. The rank is 2. The nullity is 0. 0 plus 2 is 2. And 2 is the dimension of the domain. So again, this is another example that the nullity in the kernel adds up to 2. Adds up to the dimension of the domain. Okay, let's see another example. Probably this would be the last one. Okay, for today. So for the last example, this is example 48. Though, yeah, nag-freeze yung screen, but now it's up. So I define L to be a map from P2 bracket X to P2 bracket X. So again, P2 bracket X, set of all polynomials of degree at most 2. So for any element of P2 bracket X with generic form AX squared plus BX plus C, A, B, and C are real numbers, then I will define L of PX to be AX squared plus B plus C X plus A plus B plus C. Again, it's straightforward to show that L is indeed a linear transformation from P2 bracket X onto itself or to itself. Okay, and then let's look at the kernel of L. Again, I'll take a generic polynomial in the domain, put it inside L. So pag pinlog in ko yung generic polynomial na yon kay L, ito yung makukuha kong image by definition. And for P to be an element of the kernel, I need to find conditions on A, B, and C, on these coefficients A, B, and C, such that this image will be equal to the zero vector, right? Or in this case, the zero polynomial, okay? Again, I'll just need to equate coefficients. So that means A must be equal to 0, B plus C must be equal to 0, and then A plus B plus C must be equal to 0. That's how we got this linear equation, this system of linear equations. And then we can just do forward substitution. Let's see. Oh, yeah. A is 0, so that means B plus C must be equal to 0. So if that is the case, then strictly A is 0, and C must be equal to negative B. Okay, kasi yung third equation is redundant because we already know that A is equal to 0, B plus C is equal to 0. So when you add A plus B and C, you'll just be adding the respective sides of these two equations. So this is kind of redundant, so I can just forget about it. So ang conditions lang pala talaga will be characterized by the first two equations. But this tells us that A is equal to 0 and C must be equal to negative B. Okay. If I will plug this into our generic form for P, remember P is of this form. We found out that it is necessary and sufficient for A to be 0 and C to be equal to negative B for P to be in the kernel. So what I'll do is to plug in A 0. So that's why here you don't see any x squared. And then B is a free variable, so I retain B. And then C is necessarily equal to negative B. That's how I got this. So any element of the kernel is of this form. P of x equals bx minus b, where b is any real number. Okay, b is a free variable again. But I can write this as, or I can factor out b. Or technically, we apply the distributive property of scalar multiplication over polynomial addition. So that's how we got this. Okay, and so the kernel can be written in this form. Siya lamang ay b times x minus 1 for any real number b. And at this point, it is clear to see that the kernel is any scalar multiple of x minus 1. Okay, and thus a basis for the kernel would be x minus 1. Kasi lahat ng element ni kernel ay scalar multiple lamang ni x minus 1. So therefore, the set containing x plus 1 is a basis for the kernel. Okay, again, that is because kahit anong element ng kernel ay scalar multiple lamang ni x minus 1. So this should be x minus 1. Or actually, I wrote that here. Okay, so dahil yung basis ng kernel ay isa lamang yung laman, we can say that the nullity of L is equal to 1. All right. Okay. Now let's compute for the rank. Now to compute for the rank, I will employ this trick. I will let b plus c be equal to another variable d. So that means any polynomial. Okay. So remember, para mahanap yung range, kailangan kong i-analyze ano yung itsura ng mga function values. All right. So I know that function values has this form, but I'll impose this, or I'll use this clever trick. I will use a change of variable. I'll say, okay, for the sake of what is to follow, I will replace b plus c by d. So remember, ito yung itsura ng mga elements ng range. With the change of variable, I can replace b plus c by d. So this guy can be written in this manner. Okay? And then the nice thing about this is that I can write this as this guy. Tama ba to? Okay, let me just double check. So this would be ax squared plus a plus dx plus d. So I have ax squared plus dx and then a plus c. All right. So just a clever way of rearranging terms. I got this one. Okay. And why do I like to look at elements of the range to be of this form? Well, because at this point, it's clear that any element of the range is a linear combination of x squared plus 1 and x plus 1. So my candidate for the basis would be x squared plus 1 and x plus 1. Kasi I am sure that the range is the set of all linear combinations of x squared plus 1 and x plus 1. Alright? Kasi napakita natin na lahat ng elements ng range ay linear combination lamang ng x squared plus 1 at x plus 1. Okay? Now, what's remained to be shown is that the set x squared plus 1 and x plus 1 is linearly independent. But again, by the Steinitz replacement principle, kailangan ko lang ipakita kapag meron akong set of two elements, I just need to show that one is not a scalar multiple of the other. But obviously that is the case kasi meron akong x plus 1 dito. By multiplying, if I multiply x plus 1, or no matter what scalar, I multiply to x plus 1, I cannot get x squared plus 1, right? So that means x plus 1 is not a multiple of x squared plus 1 and vice versa, making this set linearly independent. It's linearly independent, and any element of the range is a linear combination of those two guys. So therefore, the range of L is this set with basis x squared plus 1 comma x plus 1, right? Actually, I did the detailed proof here pala of the linear independence of x squared plus 1 and x plus 1, but I guess that's more elegant, the use of the Steinitz replacement principle. But nevertheless, we came up with the same conclusion that B is a basis for the range. And since the basis for the range consists of two elements, we can say that the rank of L is equal to 2. And then again, let's see if our hunch earlier is correct. The sum of the nullity and the rank is the dimension of the domain, right? Rank L is 2. Nullity of L is 1. Okay, so the sum is 3. And it just so happened that the dimension of the domain is also equal to 3. So this further supports our hunch that the sum of the nullity and the rank is equal to the dimension of the domain. Okay? And that is exactly what Theorem 25 tells us. So this is called the rank nullity theorem, that if you have a linear transformation from V to W, so the domain is V, then the rank of L plus the nullity of L is equal to the dimension of V. Okay? So Theorem 25 or the rank nullity theorem gives us a nice way on how to compute both the rank and the nullity by just computing one of them. And I guess, at least in the examples that we have met, mukhang mas madaling i-compute yung nullity ni L kaysa sa rank ni L. Kasi yung rank ni L, kailangan hanapin natin yung itsura ng range. And usually finding the range of a linear transformation is not that easy, right? Much more finding a basis for the range. So that's why usually if you can, compute for the nullity of L, look at the dimension of your domain, and just subtract the nullity from the dimension of the domain. That will give us the rank of the linear transformation. So that's the utility of the rank nullity theorem. I omitted the proof. Usually proofs of the rank nullity theorem is given in any standard linear algebra text. So, but the utility or the significance of Theorem 25 is on the result itself and not on the proof. Okay, so that's why I omitted the proof. Remark 5, or an instant corollary of Theorem 25, is that if the kernel and the range are both finite dimensional, then V is finite dimensional. And that's obvious because kung yung rank ay finite at yung nullity ay finite, then if we take their sum, then that will also be finite. So the dimension of the domain should also be finite. Okay? And then we'll end the module with Theorem 26 called Sylvester's Theorem. This tells us the property of the nullity and the rank with respect of linear transformations L and M with respect to the nullity and the rank of their composition. But I'm not yet sure if we'll be able to see Sylvester's theorem in action, depending on how far we can go with our numerical linear algebra portion. But for now, let's just state Sylvester's theorem, and then let's see if we can use it for future problems. Okay. But for now, I don't think you're going to use Theorem 26 in any of the homework problems. And there we go. I think that ends module 3. Okay. Any questions? I understand that might be too much of an information for one sitting, but unfortunately we are on a mid-year class. Supposedly this should have been 2 classes or 3 classes, but yeah, we are pressed for time here. So yeah, that completes module 4. In summary, what we module 3. In summary, what we did in module 3 is to look at linear transformations. How are they defined? We look at the structure of the collection of all linear transformations, and we said that it is another vector space with usual vector addition and function addition and scalar multiplication. That the linear transformations are usually rare relative to the set of all functions between vector spaces, especially if the dimension of the vector of the domain is much less than the number of elements in the vector space. And then what else? We showed that the composition of 2 linear transformations is another linear transformation. Which reminds me, parang mas madali pala yung proof para dun sa theorem ng M circle L is a linear transformation. So, but anyway, and then we have shown, we have met the definition of being an being a monomorphism, an epimorphism, and an isomorphism. And then we look at the kernel and the range of a linear transformation and said that they are subspaces of the domain and the codomain respectively. And as such, they do have dimensions, and their dimensions are given special names. The nullity of linear transformation is the dimension of its kernel, while its rank is the dimension of its range. And we ended up with a nice result called the rank nullity theorem, which tells us that the dimension of the domain is equal to the sum of the nullity and the rank of a linear transformation. Okay, but we have noted that computing the nullity and the rank are very tedious, especially if you will consider very crazy linear transformations. That's why in module 4 we will try to develop some easier ways on how to find the nullity and the rank. Okay, but I will invoke the meta-axiom of ignorance. I will suppose that when you are doing homework 4, you haven't seen module 4 yet. So bawal gumamit ng shortcuts from from module 4 in order to solve problems from homework 4. All right? So that's the deal. You can only use things that were proven in the previous modules for homework 4, or some elementary facts that we can assume from your previous courses. But do not use anything from module 4 in order to solve problems from homework 4. All right? Okay. Yeah, any questions? Yes, Jeng.
Sir, kasi sabi niyo po kanina, ano tawag dito? Yung range of L is mahirap hanapin. So since you've already proven the rank na the rank nullity theorem, so can we use the dimension to show or to assume the number of or the dimension of the nullity of the rank if you've already solved for the nullity? So that's a question.
Yes. Yeah, that's perfectly fine. I mean, that's the whole point of the rank nullity theorem. Kasi sabi nga natin, mahirap computein yung rank. Kasi mahirap hanapin yung range. Pag nakuha mo na nga yung range na mahirap, kailangan mo pang hanapan ng basis yung range, which is another mahirap na bagay. So for now, if I ask you to find the nullity and the rank, pwedeng hanapin nyo lang yung nullity, tapos gamitin yung rank nullity theorem para computein yung rank. So that's perfectly fine. And that's the whole point of Theorem 25. Yeah. Pero kung gusto niyo talagang pahirapan yung sarili niyo, sige, hanapin niyo yung range, hanapan niyo ng basis yung range, pero kailangan niyo makasigurado na basis talaga siya, so dapat linearly independent, saka ini-span niya yung buong range. Tapos, bilangin niyo yung elements, yun yung rank. Pero usually what we do is to find the nullity, then appeal to the rank nullity theorem in order to find the rank. Okay? But that's a nice strategy, Jen. Yeah, you can do that in the homework. Okay, other questions? Okay, if none, again, please do take some time to answer the evaluation of teachers. I think you can find it in your student portal, so I will really appreciate your honest comments or suggestions or feedback about the class. I took yesterday off, so there are a lot of submissions that came in yesterday until early this morning. So I haven't graded them yet, but I'll try to do that today. Actually, I said I took yesterday off, pero yeah, I started working again probably 10 p.m. yesterday until 4 a.m. kanina just to finish module 4. But I'll go back to grading papers perhaps later in the evening, wee hours of the day, kasi doon ako pinaka-productive. And then also kindly check for those who are eligible for markups for homework 3. Please check if I have given you the markups, because I think I have already done that for everybody eligible for the markup. But if I missed you, kindly send me a message. And then homework 4, the deadline is on Wednesday. Again, aside from the 5 problems from the module, we have 2 extra problems. So yeah. And then if you want to get a markup, so ito yung condition to get a markup for homework 4. So you need to be able to submit at least 4 out of these 5 problems. Okay? So hindi kasama sa requirements sa markups yung additional problems. So kapag nakapag-submit ka na ng 4 out of these 5 problems in homework 4, then you become eligible for the markup. But I want to make sure that you are giving up on submitting the extra problems. So before I give you the markup, you need to submit an inline submission to homework 4 markup before the deadline, saying that you want to get a markup. Pag hindi kayo nakapag-submit ng ganung message dun sa homework 4 markup assignment, then you won't be eligible for the markup. All right? So this is just a check for me to know na gusto nyo nang kumuha ng markup, even if you haven't submitted the 2 extra problems. Okay, so now I remember I still owe you a write-up of those 2 problems properly. I'll do that later today. So again, make sure to submit a text in homework 4 markup assignment in our course site, saying that you want to get the markup. Once you get at your current submission. So at least 4 out of the 5 problems must be submitted, and then plus a message in homework 4 markup para mabigyan kayo ng markup before the deadline. Otherwise, I won't give you any markup. But anyway, homework 4 is just out of 17.5 points. So that should give you a lot of breathing room in order to compensate for homeworks 1 and 2. And again, I'm thinking of reducing the number of homeworks for the course. Probably we'll have at least 6, maximum of 8 homeworks, but I'm thinking the ideal number for me would be 7. Okay, just let me know if you have any qualms with that. But other than that, that would be my plan for the semester. Okay. Now, are there any questions or concerns? If there are none, then let's call it a day. Thank you all for coming. Enjoy the rest of the day, and then let's see each other probably on Wednesday and start talking about Module 4. All right. So thank you guys. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.